This information presented in this course is based on reference materials that are believed reliable and consistent with standards accepted at the time of presentation. Possibility of human error and ongoing research and development in medical sciences does not allow assurance that the information contained herein is in every respect accurate or complete. The information presented during the course is intended for teaching of undergraduate and graduate students in biomedical education and is intended only for teaching. Students who successfully complete this course should check the product information sheet included in the package of any drug they plan to administer or dispense to be certain that the information presented in this course is accurate and that changes have not been made in the recommended dose or in the contraindications for administration. July 9th, 2014. The topic of today's lecture is covered in Chapter 27 of our textbook and includes the aliphatic and the aromatic hydrocarbons. Today we'll have a discussion about these hydrocarbons and particularly focus in on the nature of these particular agents as well as their potential toxicities. This is an outline of the topics we'll discuss today. We'll begin by talking about the composition of hydrocarbons of the various types. We'll discuss petroleum and its distillates. We'll discuss aromatic and halogenated hydrocarbons. And we'll have a very brief discussion of various methods of detection of hydrocarbons. When we look at hydrocarbons as a group, we see that they fall under the general category of organic compounds. And this is pointed out here on the flow chart to the right. As we see, hydrocarbons exist as various types. We have those which can be categorized as aliphatic and include acyclic hydrocarbons as well as alicyclic hydrocarbons. And we have those which can be characterized as aromatic. If we look at aromatic hydrocarbons, we see here below the words aromatic hydrocarbons a prototype structure, and that is the structure of benzene. And so as we can see, we have a six-membered ring with three double bonds, which allows conjugation and delocalization of electron density. Right? This is why this is considered aromatic. On the other hand, if we look at different types of aliphatic hydrocarbons, such as the acyclic alkanes, we have a straight chain of carbons and hydrogens around them. Or if we look at alkenes, we still have a straight chain that contains at least one double bond. If we look at alkynes, we have a straight chain that contains at least one triple bond. So within acyclic hydrocarbons, we have members such as alkanes, alkenes, and alkynes. If we look at the alicyclic hydrocarbons, these are going to be aliphatic hydrocarbons that are arranged in cyclic structures. So the simplest of which is cycloalkane, such as cyclohexane that you see here. Again, a six-membered carbon ring, but here no double bonds, no conjugation, no electron delocalization around the ring. We can further look down this list and see things like cycloalkenes, which would be a cyclic structure that contains a double bond, or cycloalkynes, which would be a cyclic structure that contains a triple bond. But if we look at these latter two, we see that there's no conjugation around the ring. Yes, there's pi bonding in the higher order bonding, right? So the double bond in the cycloalkene does have pi-pi bonding of the electrons. But again, this isn't delocalized around the entire ring like we see in aromatic structures. This is a simpler flow chart perhaps to keep in mind and to kind of categorize the different hydrocarbons. Particularly here we're looking at aliphatic hydrocarbons. And we see that those that have all single bonds would be considered alkanes. Those with one double bond would be alkenes. Those with one triple bond would be alkynes. And then, if we have cyclic forms of these aliphatic hydrocarbons, we'd call them, for example, cycloalkanes or cycloalkenes or cycloalkynes. And so these are all different types of aliphatic. And the major difference between the aliphatics and the aromatics is that the aromatic hydrocarbons allow nice electron delocalization around a ring structure. Okay, so by the end of this slide, you should feel comfortable knowing in general what a hydrocarbon is. And the three major types of hydrocarbons, which include the aliphatics, the alicyclics, and the aromatics. The aliphatics are sometimes called acyclics, and they are composed of straight open chains. The alicyclics are composed of ring structures that are generally saturated. Okay, so no or few double bonds. And the aromatic hydrocarbons are those which are ring structures, planar rings, that contain unsaturated bonds, multiple carbon-carbon double bonds, like we see in the structure of benzene. These are some sample aromatic hydrocarbons. We see in the upper left the simple structure of benzene, a six-membered ring with three double bonds. If we then look to the right, we see a substituted benzene, an analog of benzene, which is known as toluene. Toluene has a methylation of the benzene ring, right? So it's basically a methylbenzene called toluene. If we look over to the right again, we see a second methylation event on the benzene ring, giving us xylene. If we look down at naphthalene, we see that that's two fused benzene rings. Or if we look at biphenyl, we see that it's two benzene rings that are separated by a carbon-carbon single bond, as opposed to naphthalene, which is connected by a carbon-carbon double bond. If we look at phenanthrene, we see it's three benzene rings. And if we look at anthracene, we see that it's two fused benzene rings with a third ring fused to it that has two double bonds. And so the point here isn't so much to have you memorize different structures, but to be able to look at these structures and realize that these would be considered aromatic hydrocarbons. Hydrocarbons because all we've got here are hydrogens and carbons, and aromatic because we have a lot of pi-pi bonding and conjugation around the ring structures. The majority of hydrocarbons that we encounter, either in the occupational setting or in daily life, are actually obtained from crude oil and are characterized as distillates of petroleum. If we look on this cartoon sketch, we see that a typical barrel of crude oil, which is made up of 42 gallons of material, is generally converted into about 20 gallons of gasoline, about 10 gallons of diesel fuel and heating oil for homes, about 4 gallons of jet fuel, and then we have the remainder of these products coming out of crude oil, being things such as heavy fuel oil or liquefied petroleum gas or other types of distillates that are used in some very common products that we encounter every day. Things such as various plastics such as those in bottles, those in chairs, those in shoes, and various types of products, even baby bottles. Okay, so petroleum distillates, whether we think of them often or not, are very ubiquitous in our world, and in a lot of cases make our lives more convenient, make things more convenient for us. And so many of the hydrocarbons that we're going to discuss today are considered to be petroleum distillates. And so crude oil is taken and it's distilled, and different fractions produce different types of hydrocarbons, or liberate different types of hydrocarbons. And so as you see, as we go forward, there's going to be some slides and some flowcharts that show you the different types of distillates we get out of crude oil. And those are not going to be meant to explain everything about all the distillates, but rather just give you a big picture approach as to all the many compounds that are extracted out of crude oil that have utility for us on a day-to-day basis. So as we prepare to discuss petroleum distillates in more detail, just a little bit of humor now to get you ready for that discussion. So that 42 gallons of crude oil that gets converted into various useful energy sources and starting materials for the development of things like plastics or other products. Where does it come from? How do we convert that crude oil into all of these goodies? Well, the answer is the crude oil gets distilled, and different fractions give us different types of hydrocarbons. And so the next slide I'm going to show you here explains the process. So if we look way up at the top, in the top left, we'll start with crude oil, in the very upper left corner. And if we follow that box, we see it desalted, it enters into a distiller, and then there's a whole plethora of different distillates and separation methods that are used. And so the point of this isn't really to get into all of that, but really to look over towards the right, way on the right, and what you see there is that you get all kinds of distillates out of crude oil that are useful. Things like fuel gases, liquefied petroleum gas, aviation gasoline, automotive gasoline, which many of us have recently put into our cars to get to campus. Many solvents, kerosene, and as we go further down the list, we see various lubricants, greases, waxes, things that are used as starting materials to produce plastics and such. So petroleum distillates are very useful in modern society, and they are the primary source of hydrocarbons that we encounter. And so if we now look at crude oil and we break it down into its distillates, there's really two general types. There are the hydrocarbons and the non-hydrocarbons. The non-hydrocarbons are depicted here for you on the right, and they include various types of compounds that contain things like sulfur, or nitrogen, or oxygen, or even metals. But we're going to focus today on the hydrocarbons depicted there on the left. And as you can see, from crude oil, we obtain hydrocarbons of the aliphatic type, of the aromatic type, and another type of aliphatic, the naphthenes, which are the cyclic alkanes. Okay, so we have the aliphatics, which are straight chains or branched chains, as you can see there way on the left, anywhere from 1 carbon in length to 60 carbons in length. If we look at the naphthenes, which is just a synonymous term for cycloalkane. Here we have cyclic saturated rings that are classified here as hydrocarbons. And if we look in the middle portion, we see aromatic hydrocarbons that are also obtained from crude oil. So crude oil is a rich source of many types of compounds, hydrocarbons included. Of the hydrocarbons found in crude oil, we have the aliphatics, the acyclic aliphatics, such as the long chains or the branched chains, the alicyclic aliphatics, such as the cycloalkanes, and then the aromatic hydrocarbons, where we have conjugated double bonds. So, by this point in the lecture, you should feel comfortable knowing the difference between an aliphatic hydrocarbon, such as a acyclic alkane, a cycloalkane, which would fall under the broader class of alicyclic hydrocarbon, and aromatic hydrocarbon. So do you feel comfortable knowing the difference between aliphatic, alicyclic, and aromatic in terms of the hydrocarbons? Because this will now form the basis of our discussion as we move forward. Now, before going into all of the toxicology discussion of the various hydrocarbons, I came across this paper that was recently published that looks at microbes and how they degrade hydrocarbons. Microbial hydrocarbon degradation. Efforts to understand biodegradation in petroleum reservoirs. And so this was a report recently published that looked at microbes and the ability of microbes to take hydrocarbons and use them and get rid of them from the environment. And so this would be particularly useful in chemical spills where you have oil spills, like we had a couple years back with that big BP oil spill. Having microbes that could eat up some of these hydrocarbons would be very useful in helping to clean up spills. Now, we're definitely not there yet, but just to show you some of the data that's been compiled on this topic, I wanted to spend a second or two. And so here you've got different types of microbes, both aerobic or anaerobic, that can take hydrocarbons and activate them. And what we mean by that is actually use them in metabolic processes. So, for example, there are microbes that are able to take short-chain non-methane alkanes and convert them into various metabolic processes. Well, not really convert them into processes, but use them as substrates during metabolism. And so, for example, if you look there at the anaerobic microbes, they can add fumarate to these particular compounds and use them as substrates for energy metabolism. In addition, we see long-chain alkanes and aromatic hydrocarbons that are substrates for enzymes. In bacteria, those bacteria can use up those hydrocarbons for various metabolic processes. Another way to look at this is with this flowchart, also from this same publication. At the very top, you can see aliphatic hydrocarbon, aromatic hydrocarbon, and how it's processed through aerobic routes or anaerobic routes. But basically what you see is if you follow those light blue boxes all the way down to the bottom of the flowchart, you see energy production. Okay, so you see beta oxidation and the TCA cycle. And so this is an interesting idea, the use of microbes to eat up hydrocarbons that may have found themselves in environmental settings that they weren't intended to be in. Again, I digress a little bit from the main topic at hand, but just to show you some interesting research along the area of petroleum distillates, hydrocarbons, and microbes. But now getting back to the toxicology of the hydrocarbons. And so hopefully you've printed out these slides and now you can take some notes. Just wanted to give you a little bit of a background on hydrocarbons in terms of exposure routes, use and abuse of these compounds. So now these compounds are primarily encountered through inhalational exposure, occasionally through oral ingestion, occasionally through transdermal absorption, but particularly common is the inhalation route. Just to give you some numbers, and now these numbers are getting a little dated, but they're from our textbook, and they report that in 2001, in the United States, there was approximately 65,000 hydrocarbon-related exposures that resulted in hospitalizations. Of that 65,000, 99% of them were accidental exposures. And in addition to that, 65% of them involved children who were less than 5 years of age. And so hydrocarbon exposure and hospitalization is not unusual, is not uncommon. And so why? Why does this happen? And before we kind of get into the toxicity, I wanted to also kind of report on the intentional exposure. So this idea of being exposed to hydrocarbon, is it intentional, is it unintentional? Well, intentional inhalation has been admitted by adolescents and drug abusers in various surveys. And so, quoting a survey from 2006, about 8% of 8th grade students that were surveyed admitted to using inhalants during the past 12 months as a way of getting intoxicated. So we have unintentional exposures that can happen, for example, through consumption, a child getting their hands on a paint thinner, for example, or something happening in a work setting. But then you have intentional exposure meant to intoxicate. And so there's a problem with that because the hydrocarbons that are abused tend to be the volatile ones that get deep into the lungs. They're found in paint adhesives, in paint thinners, in cigarette lighter fluid. And they're abused in such a way that a large concentration of the hydrocarbon is inhaled. And there have been various types of toxicities associated with exposure to high concentration of hydrocarbon. And so these include things such as mild agitation, to intense hallucination, to delusion. That could progress to stupor or seizures. There's also been reports of increased risk of cardiac arrhythmias, and some people have actually died from inhalation exposures to some of these hydrocarbons. And so abuse of hydrocarbon inhalation is a public health concern. Now, not all hydrocarbons are equal in terms of toxicity, and I'm going to mention that as we move forward. In general terms, aliphatic and alicyclic hydrocarbons tend to be gases or liquids, and they're generally considered non-toxic or to have low toxicity. But the biggest concern with them is the fact that they're inhaled and they're competing out oxygen from the lungs. So basically what happens is you have a lowered oxygen content in the inspired air, and that leads to a decreased oxygen availability for gas exchange. Okay, so generally speaking, the aliphatic, the alicyclic hydrocarbons are low on the toxicity end, but when they cause toxicity, often involve basically depleting oxygen in the lungs. No antidote is available, other than just supportive care. On the other hand, aromatic and halogenated hydrocarbons have been associated with acute systemic toxicities. And we've got the whole gamut of toxicities here: hematological, hepatic toxicity, renal toxicity, CNS effects ranging from mild agitation to depression to loss of consciousness or in some patients hallucination or seizure. And then we have cardiovascular events, increased risk of arrhythmia. And why is that? Well, the mechanism for that seems to be that the high concentrations of hydrocarbons actually sensitize the myocardium and make it more responsive to catecholamines. And this is particularly true of aromatic and chlorinated hydrocarbons. Okay, so there are some serious concerns associated with hydrocarbon exposure, particularly with respect to the aromatic and the halogenated hydrocarbons. And if you're wondering about the halogenated hydrocarbons, we haven't gotten to them yet in terms of their structures. But they are the last type of hydrocarbon we'll discuss in the chapter, so I've kind of gotten a little bit ahead of myself. Okay, so in terms of things you should think about with regard to exposure, okay, you have unintentional versus intentional. Major route of exposure being inhalation. Aliphatic and alicyclic hydrocarbons generally causing toxicity acutely because of the, lowering oxygen into the lungs. On the other hand, aromatic or halogenated hydrocarbons having some significant systemic toxicities associated with them. And so we worry about use and abuse of these types of hydrocarbons because of the threat they pose, particularly in terms of CNS effects and cardiovascular effects. In terms of the mechanism of toxicity now of the aliphatic and the alicyclic hydrocarbons, again, I've mentioned that these generally are considered to be on the low end of toxicity and reactivity. We can classify them as being similar to pulmonary irritants or simple asphyxiants, which can impair oxygen content in the lungs and then in the blood. The degree of cyclization or unsaturation doesn't seem to correlate with toxicity, and at very high concentrations can cause anesthetic-like action and some of the other toxicities we've mentioned. These compounds tend to be mostly flammable or combustible, and we're going to now focus in on a few of them. I've mentioned them here on the top of the slide, so hopefully you'll be taking some notes. In terms of their properties, their sources, the kinds of uses they have, and then the specific toxicities associated with each. So for example, if we look at methane, in terms of its properties, it's flammable, and it's odorless and colorless. Okay, so methane is flammable, it's odorless, and it's colorless. It's derived from the Earth's crust, right? So it's a natural gas that we get from the Earth's crust and also from large landfills. It's mainly used as heating fuel or in the production of other types of gases. And generally speaking, it's not considered poisonous in terms of a specific poisonous mechanism, but can cause death due to oxygen deprivation. Right? So it's considered a simple asphyxiant. When it comes to butane, butane is a flammable, colorless gas. It's mainly found in nature as a gas, and it's also released during petroleum cracking, which is part of the distillation process. Its major industrial use, and we're talking about N-butane, normal butane, is as motor fuel or as propellant, or often used in the research lab for organic synthesis. So here as fuel for various types of motor vehicles, as propellant, or as starting material in organic syntheses. Again, N-butane is considered to be a simple asphyxiant. At high doses, very high exposures, has been found to cause narcosis or sleepiness. Octane, normal octane, 8 carbons long, flammable colorless liquid. It's derived from crude oil through the cracking process, and it's used in gasoline. So here, its major use is as a solvent or as a fuel, and it's got low acute toxicity, but is capable of causing CNS depression and irritation of the pulmonary system. Okay, last but not least, in this particular set, we'll talk about propane. Propane is a flammable colorless gas. It's also primarily derived from petroleum. And it's got several industrial uses or household uses. It's used as a fuel, it's used as a refrigerant, and it's used as a material in organic syntheses. Again, its major mechanism of toxicity is oxygen deprivation, so it's considered a simple asphyxiant. And at high doses, like butane, can cause narcosis or sleepiness. Okay, so here we've talked about 4 aliphatic hydrocarbons. We've talked about their properties. We've noticed that they're all flammable. We've talked about where we get them. And they're all coming either out of nature itself, like methane, or from the distillation process of crude oil. We've talked about the various uses, and we've talked about the toxicities. And what we've seen here is most of these have an asphyxiant property. They deprive oxygen, take up the space that oxygen will otherwise take up in the lung. And some of them cause sleepiness or narcosis. Okay, so hopefully you've gotten a chance to write those things down. If not, make sure you go back over these 4 particular examples of aliphatic hydrocarbons in terms of property, sources, uses, and toxicity. The alicyclic hydrocarbons that we'll now discuss include cyclohexane, cyclopentane, and cyclopentadiene. Cyclohexane is a flammable colorless liquid obtained from crude oil as a distillate. It's used as a solvent for paints and various resins, and also used in organic synthesis of various compounds. It exhibits low acute toxicity, but it can cause CNS depression and is volatile enough to cause pulmonary irritation. Okay, so while it's a flammable colorless liquid, it does have some volatility associated with it, causing low acute toxicity, but in some people, pulmonary irritation or CNS depression. Now, cyclopentane, which is just 1 carbon less, still a ring structure, but now a 5-membered ring, is also a flammable colorless liquid, also a distillate of petroleum. But cyclopentane has several uses. It's used as a solvent. It's also used in the shoe industry, and it's used in the process of wax extraction. When wax is being produced. Right? So the manufacturing of wax is used in the shoe industry. It's also used as a solvent. Cyclopentane has low acute toxicity, but has been found to cause CNS and respiratory depression, and has an ability to irritate the respiratory tract. So it's a pulmonary irritant. So again, cyclopentane, a flammable colorless liquid obtained from crude oil as a distillate, used as a solvent, used in the shoe industry, used in the production of wax. Low acute toxicity, but does cause CNS and respiratory depression in high concentrations, and serves as a pulmonary irritant as well. Now, cyclopentadiene. It looks a lot like cyclopentane, but it's got one double bond in that 5-membered ring. This one's a flammable colorless liquid as well. It's a distillate of crude oil, but this one's used in various types of industrial or household settings. Used in resins, used in production of camphor oil, and it's also used in the preparation of metals. So used in the metal industry. Resins, production of camphor oil, and in the preparation of metals. Now, cyclopentadiene has been found to be a pulmonary irritant in rodents. That's its major toxic effect. No major toxicities in human. Again, at high enough concentration, you can cause deprivation of oxygen, and a person can pass out. But primary toxicity is in rodents. So cyclopentadiene, flammable colorless liquid, obtained from petroleum, used in resins, camphor, and preparation of metals, and is a pulmonary irritant in rodents. Turning our attention now to the aromatic hydrocarbons. Now these hydrocarbons, particularly at high concentration, can cause CNS effects such as CNS depression, sleepiness, or narcosis, and that can, in some patients, progress to hallucinations or to convulsions. Some of the aromatic hydrocarbons are known or suspected human carcinogens. But in terms of acute toxicity, again, we're going to see minimal effects except at very high concentrations. In terms of their chemistry, aromatic hydrocarbons form explosive mixtures with air and are flammable and have low flash points. They are able to react with oxidizing agents. They have moderate to strong aromatic odors. And by the EPA, they're designated as priority pollutants or hazardous waste. So now I'm going to spend a little bit of time talking about a few specific aromatic hydrocarbons. We'll start with benzene. Benzene is a flammable colorless liquid. It's derived from petroleum. It's also derived from coal tar. It's also found in landfills. It's used as a solvent. It's used in dye and paint production, and it's also used in organic synthesis. The toxicity of benzene is well studied, and so the acute human toxic effects include things like pulmonary and dermal irritation, sleepiness, or at very high exposures, convulsions. Chronic toxicity of benzene is primarily hematotoxic. So we see blood toxicities, we see effects on the bone marrow. So chronic toxicity or chronic exposure to benzene can cause bone marrow suppression. It's also capable of causing CNS depression, dermal irritation, and respiratory toxicity. Okay, so that's also related to the fact that while it's mostly liquid, a portion of it exists as vapor and can be inhaled. So again, benzene is a flammable colorless liquid. It's found in coal tar. It's found in landfills. It's a petroleum distillate. It's used as a solvent. It's used in the production of dyes and paints or in organic syntheses, and has both acute and chronic toxicities. Now, naphthalene is a white crystalline substance. So it's a solid at room temperature. It's used, it's derived from petroleum or from gasoline, and it's the major constituent of mothballs. So it's used as a moth repellent. It's also used in dye production. It's been used in explosives and in lubricants as well. It has acute toxic effects that include pulmonary and dermal irritation, narcosis or sleepiness, and if consumed by mouth has been found to induce hemolytic anemia. Chronic toxicities of naphthalene have been reported in terms of ocular toxicity and particularly ocular opacity, right, causing disruption in vision. So again, naphthalene is a white crystalline substance. It's often described as a flake, white crystalline flake. It's derived from petroleum or from gasoline. It's used as a moth repellent. It's used in dyes. It's used in explosives or in certain lubricants. And it has both acute and chronic toxicity, acute being pulmonary dermal irritation or narcosis, sleepiness, or hemolytic anemia by oral ingestion. Chronic toxicity involves ocular effects, particularly ocular opacities. Now, toluene. Toluene is a flammable, colorless liquid. It's derived from coal tar. It's derived from petroleum. It's derived from gasoline. It's used in the production of benzene. It's used in the production of dynamite, TNT. It's also a solvent. Acute toxicities are similar to that of benzene, but chronic toxicities appear to be less than that of benzene, so less likely to cause bone marrow suppression, for example. So again, toluene is a flammable, colorless liquid derived from coal tar or petroleum or gasoline. It's used in the production of benzene synthetically, in the formation of TNT, dynamite. It's also used as a solvent. And its acute toxicity is similar to benzene. Its chronic toxicity seems to be less severe than that of benzene. Now, anthracene. Anthracene is an organic compound, aromatic compound, sometimes described as green oil, but in fact is a solid. It exists as a green crystal. It's used in the formation of dyes, and it generally exhibits low toxicity. Its carcinogenic potential is unknown. Benzoapyrene exists as yellowish crystals derived from coal tar or petroleum or gasoline, also present in smog and tobacco smoke. Its acute toxicity appears to be low, but it is a known mutagen. It's a pro-carcinogen, which means it has to be activated by metabolism to become a carcinogen. And in animals, it has teratogenic effects. So benzoapyrene is a known mutagen. It's a pro-carcinogen, so it gets converted to a carcinogen through metabolism, and it's been found to be teratogenic in animal species. I wanted to make a correction concerning toluene. I mentioned that toluene can be used to make TNT, but in fact I mixed the concepts that TNT and dynamite are the same. Okay, and so I want to be clear that they're not the same. Dynamite is a highly explosive material that contains nitroglycerin, which is soaked in a substance such as clay. And so the difference between TNT and dynamite is that TNT is a chemical compound, whereas dynamite is a mixture. TNT is trinitrotoluene, and it's highly explosive, but it's a different substance than dynamite. Dynamite contains nitroglycerin. If we look, TNT contains about 4.2 megajoules per kilogram, while dynamite contains 7.5 megajoules per kilogram. So dynamite's more powerful explosive, although they're both quite powerful. TNT is more stable than dynamite, and TNT is used by the military because it is more stable than dynamite. Okay, so I don't mean to make a big deal about it, but I had called TNT dynamite in the preceding slide, when in fact TNT is a chemical and dynamite is a mixture. So hopefully I've clarified that now. We'll now turn our discussion to the halogenated hydrocarbons. In this group of molecule, one or more of the hydrogen atoms is replaced by a halogen atom, such as a fluorine, a chlorine, a bromine, or an iodine. We see halogenated hydrocarbons all around us. They're used as solvents, they're used as refrigerants, they're used as fire retardants. Now, the mechanism of toxicity is going to occur following exposure by inhalation or oral ingestion or dermal, as we've seen with the other hydrocarbons. At high concentrations, CNS effects such as drowsiness or incoordination will be observed, or GI toxicities such as nausea and vomiting. But at very high concentrations, we can see hepatic, renal, and cardiac toxicity, and increased risk of death due to very high exposures. Now, the halogenated hydrocarbons range from non-combustible to highly flammable gases or liquids. They react violently with alkali metals and oxidizers. And so let's talk a little bit about halogenated hydrocarbons and their effects. Before we finish, we'll also talk about methods of detection. And so maybe we could do that now before I get into the structural discussion. So actually, before we get into the toxicity and the structures of these compounds, let's talk a little bit about how they're detected. And really, the general way here is GC, okay, gas chromatography. It's sensitive to detecting hydrocarbons in the air, in the soil, biological samples such as plasma, because hydrocarbons tend to be of high volatility. So GC is a good method for this, often coupled to either electron capture detectors or flame ionization detectors, but more recently mass spectrometry has has taken over. So GCMS, as that's sometimes referred to. So halogenated hydrocarbons and other hydrocarbons, petroleum distillates, as we've seen, are generally flammable with high vapor pressures, low flash points, which makes them easily separatable by GCMS. Now, the essential feature of chromatographic methods like GC is the ability to separate, to elute, and to resolve. And so oftentimes in the GCMS setup, we'll have the capillary glass column and the headspace analysis. Methyl silicone is the nonpolar stationary phase, helium as the gas carrier, and then various organic solvents are used for sample extraction. Now again, I'm not here to go into a very complicated explanation of how we can detect these hydrocarbons, but our textbook has mentioned the use of gas chromatography coupled to either FID, flame ionization detector, ECD, electron capture detector, or to a mass spectrometer. Okay, so that's basically all we're going to talk about when it comes to the methods of detection. Now we're going to talk about the composition of the halogenated hydrocarbons and their toxicities. This slide contains many structures of hydrocarbons that contain a halogen substitution. In particular, here we've either got one chloro group or two chloro groups on the various polycyclic aromatic hydrocarbons. As we can see, there's high degree of aromatization here, so these can be classified as aromatic hydrocarbons that are halogenated. And many of these compounds are encountered in industrial use. If we look over to the structure in the upper right, which is just flown into the screen, we see the structure of dioxin. And this happens to be 2,3,7,8 tetrachlorodibenzo P-dioxin, also known as TCDD. And if we look at the structure of TCDD, we see that it's not strictly a hydrocarbon that's halogenated, right? Because we have a dioxin structure here, two oxygens coordinating this molecule. But the structure of dioxin and that of halogenated hydrocarbons are rather similar. Okay, all the compounds on the left don't contain any oxygen. It's just carbon and hydrogen and now a halogen, right? All the ones in black. If we look at the upper right and we look at dioxin, what we see now is not just carbon and hydrogen and a halogen, but we have oxygen. But nonetheless, if you compare the structure of dioxin to that of some of the compounds here on the left, you'll see that there are some similarities. And that's important because I want to talk a little bit about the toxicity of dioxin here. Now you can have a whole 2-hour lecture on dioxin, so very briefly going to just introduce dioxin and how it works, because many of the ligands on the left will also do something similar to dioxin in the liver. So let's talk about that now. So if we look here at several of the structures depicted, now we have dioxin in the upper left corner, and we have some representative compounds like a PCB 126 pentachlorobiphenyl, right? So that's a halogenated hydrocarbon. That's biphenyl that's been chlorinated 5 times. We see the polycyclic aromatic hydrocarbons of benzoylpyrene. We see another polycyclic aromatic hydrocarbon, DMBA. And then we see another dioxin-like structure down here in the bottom left. Okay, so what this slide is showing you are all compounds which are capable of binding to the AH receptor. And the AH receptor is called the aryl hydrocarbon receptor. And it was first identified as the receptor for dioxin. And we now know that there are many ligands, some of which are hydrocarbons, that are able to activate that receptor as well. And so activation of that receptor may contribute to the toxicity of some of the particular hydrocarbons that serve as ligands for the receptor. If we look at this slide, we have a hypothetical cell, let's call it a hepatocyte. And we have a ligand that diffuses into the cell and binds to something called the AH receptor. The AH receptor is found in the cytoplasm. And when the ligand binds to the receptor, 2 inhibitory proteins called HSP90 dissociate from the receptor. Right, so normally when the ligand enters, it binds to the receptor, the HSP90 groups are lost, and now the ligand-bound AH receptor translocates into the nucleus of the cell. Do you see that here? And it associates with a third protein called ARNT. ARNT stands for AH receptor nuclear translocator. So, the ligand bound to AH receptor and bound to ARNT sit down on a xenobiotic response element, which is a region of the gene, the promoter region, that is now going to result in transcription of the gene immediately proximal to it. Okay, so we've talked about transcriptional activators a little bit earlier in the course, but here we're going to specifically now talk about halogenated hydrocarbons and also TCDD, a dioxin, able to enter the cell, bind to the AH receptor, translocate into the nucleus, form a complex with the ARNT protein, and sit down on the xenobiotic response element, which is immediately proximal to dioxin-sensitive genes. Okay, so what this slide is telling you is that certain halogenated hydrocarbons, particularly some of the ones listed on the previous slide, as well as dioxins, are going to affect gene transcription, right? Going to have nuclear effects. Now, dioxin, also known as TCDD, is one of the most toxic chemicals known to man and is a contaminant in the manufacture of the herbicide 2,4,5-T. It persists unchanged for years in the environment, and it's released into the environment by incinerators of trash, by fossil-fueled powerhouses, by gasoline-powered vehicles, by fireplaces, by charcoal grills, and by cigarettes. Even paper products contain trace amounts of dioxin, which are produced during the chlorine bleaching of the wood pulp to make the paper. Now, in terms of its toxicity, well, it's very complex. We know that it causes skin eruptions or chloracne in humans. We know that chemical workers who have been exposed to it for over a year have a higher mortality rate from cancer than people who haven't worked with it. For years and years, it was considered to be a suspected human carcinogen. And in 2012, the World Health Organization and the Institute, the IARC, the Institute, man, I should know what that means. Research carcinogen, the Institute. Well, I'll look that up in a moment. I can't remember what it means right now, but it's a big agency, which is a major agency involved with classifying carcinogens. So in 2012, the IRC has classified it as a human carcinogen. A lot of epidemiology evidence suggesting that it causes cancer in human, but also liver toxicity in human. A lot of epidemiology studies that have linked dioxin and increased risk of certain cancers, leukemias, for example. Definitely, clearly immunotoxic in man, dermatotoxic in man. In terms of animals, there's higher than normal rates of birth defects and stillbirths in rats and mice. Doesn't seem to be true in human, but strong evidence of teratogenic effects in rodents. Also, birth defects such as cleft palate, liver abnormalities, immunosuppression, atrophy of the thymus in guinea pigs. Guinea pigs are highly susceptible to dioxin's effects. They get hepatocellular carcinomas. So, what can we say about dioxin? Well, we now know that it's a human carcinogen, which is interesting because it itself doesn't cause genotoxic effects, right? It's not mutagenic per se. but evidence exists to implicate it with carcinogenicity. And we do know that it causes chloracne or dermatotoxicity, which I'll show you in the next slide. Again, let us not forget the endocrine disruption that dioxins are known to cause, their estrogenic effects. Also, IARC stands for the International Agency for the Research on Carcinogens. Okay, and they've recently classified dioxin as a human carcinogen. Okay, in conjunction with the World Health Organization. So a lot of epidemiology suggesting that, but again, no direct genotoxic effect, which is interesting. But again, I'm not meant to have a whole diatribe here on dioxins, but I do want to mention that in humans, we clearly can see the effects of dioxin poisoning in the skin. This is a picture of the former president of the Ukraine on the right, before being poisoned with dioxin, and on the left following poisoning by dioxin. And so dermatotoxic effects in human are quite dramatic. Within the topic of halogenated hydrocarbons, it's worth taking a moment to discuss chlorinated fluorocarbons. Chlorinated fluorocarbons are depicted for you here in the upper left panel. We see in the leftmost structure a compound that looks like methane, but all the hydrogens have been replaced with halides, with chlorines and with fluorines. So this compound is called a chlorofluorocarbon. The structure to the right of it is called tetrafluoroethane. And you can see this is a hydrocarbon that's been halogenated. Right? A hydrocarbon that's been halogenated. So this is why we're talking about CFCs, or chlorinated fluorocarbons, in our lecture today. These compounds are used as refrigerants, as flame retardants. They're quite ubiquitous in industry. If you look to the right, you see a cartoon diagram of the mechanism by which CFCs deplete the ozone layer in the atmosphere. And so CFCs have been under fire, okay, because of the concern of ozone depletion. So if we look in the upper left panel of that cartoon diagram, we see a chlorofluorocarbon. Right? We see a carbon substituted by 1 fluorine and 3 chlorines. And now it's exposed to ultraviolet radiation in the atmosphere. And that causes a chlorine atom to break away, and the chlorine atom collides with an ozone molecule and steals an oxygen from the ozone, the O3, to form chlorine monoxide and leave behind regular oxygen. So that ozone layer, which protects us from UV, is now being depleted by CFCs in the atmosphere. So some of the common CFCs are kind of known more by its trivial name or its common name. Freon, you may have heard of Freon. Well, there's different types of Freons, and these are used as coolants for refrigeration, air conditioning systems, and so on. And so there are various Freons with various formulas, but if you look over to the right, you can see that these are chlorofluorocarbons of varying, compositions, but C, F, and Cl are present in these molecules. Okay, so some of the common CFCs include trichlorofluoromethane, dichlorodifluoromethane, and chlorotrifluoromethane listed for you here. Again, I'm not here to have you memorize the names, but I do want you to know in basic terms what a CFC is, how it's related to hydrocarbon. It's a type of halogenated hydrocarbon, and how it can interact with ozone. We're going to talk about a few specific halogenated hydrocarbons now in the next slide. Now, none of these hydrocarbons that we're going to talk about here are CFCs. Okay, these are just standard halogenated hydrocarbons. And what can we say about halogenated hydrocarbons? Well, again, the hydrogen atoms, one or more, are replaced by a halogen like a fluorine or a chlorine or a bromine. The major mechanism of toxicity is inhalation, and at very high concentrations we can see fatality, we can see hepatotoxicity, renal toxicity, cardiotoxicity. So I wanted to spend a little time talking about some of the halogenated hydrocarbons. These are sometimes called halocarbons. Okay, and we're going to start by talking with chloroform. Now, chloroform is a non-combustible, colorless liquid that has a sweet odor associated with it. Okay, it's a non-combustible, colorless liquid. Again, you may have to write down some notes here on this slide. So it's a non-combustible, colorless liquid. It's used as a solvent for paints and as a degreaser and as a refrigerant. And in the old days, over 100 years ago, was used as an anesthetic agent. Now, acute toxicity includes dizziness, CNS depression, hallucinations. You can have observation of fatigue, headache associated with acute exposure to chloroform. Chronic exposure is more of a problem. Hepatotoxicity and nephrotoxicity have been associated with chloroform exposure. CNS effects such as hallucinations, cardiac toxicity. Chloroform is actually a suspected human carcinogen, and it's a known animal carcinogen. Okay, so that's one type of halogenated hydrocarbon. The next one I'd like to talk about is halothane. This is also a non-combustible, colorless liquid with a sweet odor, halothane. It's used as a general clinical anesthetic. It causes CNS depression and anesthesia. Can also cause ocular irritation acutely. And chronic toxicity involves hepatotoxicity. Okay, so a non-combustible colorless liquid used as a general anesthetic acutely will cause CNS depression and anesthetic action, but can cause ocular irritation as well. And chronically, you are concerned about hepatotoxicity. The next compound I'd like to talk about is methylene chloride. This is a non-combustible, colorless liquid used as a solvent for paints and as a degreasing agent. Its major toxicity is associated with inhalation. It causes pulmonary irritation, has a mild CNS depressant action, so can cause sleepiness or narcosis. It's also known to be associated with headaches. But in chronic toxicity, you worry about, with methylene chloride, hepatotoxicity and carcinogenicity. So methylene chloride is an animal carcinogen and a suspected human carcinogen. Okay, so methylene chloride, colorless liquid, non-combustible, used as a solvent for paints and as a degreasing agent. And major toxicity would be that of chronic toxicity, which can affect the liver and which is a suspected human carcinogen. Now, vinyl chloride. Vinyl chloride is a flammable, colorless gas. It's used in resins, in plastics, and as a refrigerant. Acutely, it can cause mild anesthetic effects, sleepiness, and dizziness. Chronically, it can cause hepatotoxicity or nephrotoxicity. It's a known human carcinogen as well as an animal carcinogen. So vinyl chloride, some nasty stuff. It's a flammable, colorless gas. It's used in resins and in plastics and as a refrigerant. And chronic exposure can lead to cancer development and is a known hepatotoxicant. The next compound on the list is hexachloronaphthalene. Now, hexachloronaphthalene is a non-combustible yellow solid. It is used to insulate electric wires or to lubricate. So it's an electric wire insulator, also used as a lubricant. Toxicity is mostly acute and has been found to induce chloracne and dermatitis. If ingested, may cause nausea and can cause CNS effect of confusion. So again, hexachloronaphthalene is a non-combustible yellow solid. It's used as an insulator of electric wires and as a lubricant. It's been associated with chloracne and dermatitis as well as nausea and confusion. The last halogenated hydrocarbon that I'll discuss is chlorobenzene, which is a flammable, colorless to slightly yellow looking liquid. It has an almond-like odor to it. It's used as a solvent and also in the manufacturing of phenol. Its acute toxicities are generally low, ranging from mild anesthetic action to sleepiness to dizziness, and is known to be an animal carcinogen. Okay, so chlorobenzene is an animal carcinogen, a suspected human carcinogen, but generally low toxicity upon acute exposure. Again, it's a flammable, colorless to yellowish liquid with an almond-like scent, and is used as a solvent as well as being used in the manufacture of phenol and of aniline. Okay, so hopefully you've gotten down some of the basic properties, sources, uses, and toxicities of these particular halogenated hydrocarbons. Also, you can refer to your textbook for some of this information. So that brings us to the end of Chapter 27. Again, the chapter provides a very broad overview on aliphatic and aromatic hydrocarbons as well as halogenated hydrocarbons. And we've talked about some of the general toxicities, and in each subtype we've used specific examples. So we've talked about specific examples of aromatic hydrocarbons, of aliphatic hydrocarbons, and of halogenated hydrocarbons. So be comfortable in understanding the general properties and toxicities of those particular examples as you prepare your studying towards the next exam. If you have any questions, we can address them in class, or if they are relatively straightforward, you can send me an email and I can try to respond to it via email. So again, this is the end of Chapter 27. Thanks for your attention, and I will see you soon.